Hello and welcome to this manufacturing systems technology module 12. We had in the last module discussed how to fit the Herbert cubic spline polynomial to 2 points and did a practical example where we mapped 2 points with their slopes according to variety of family of curves, variety of different curvatures were involved in fact plotting those curves between the 2 endpoints. So we had discussed last time that it is very difficult for and unrealistic actually for metrology to define the slopes of certain coordinate points, particularly when the topology becomes very complex. And therefore, can we have an equation or a fit where really without considering the slope also we would be able to vary and manipulate the curvature of the curve between the 2 points just in the same manner as we did earlier in the Hermite cubic spline. So answer to that is this new curve fit which is known as the Bezier curve fit, and the Bezier curves are based on approximation techniques that produce curves which do not pass through all the given data points except the first and the last control point, although there is a contribution from the various other data points to the overall curvature of the curve passing through the set of points actually. So the Bezier does not require a first order derivative, and therefore we can do away with the slope at a certain point, which was a major practical problem when we talk about Hermite spline earlier. And the shape of the curve is controlled only by varying the control points as illustrated here. So let us look at how such controls or how such kind of a curve fits can be obtained. So we consider here one segment of the curve, and for n plus 1 control points the Bezier curve now is defined by a polynomial of degree n which is written as Vt equals sigma I varying between 0 and n Vi b I n a function of t is the parameter where t varies again between 0 and 1, and Vt is the position vector really. So Vt is the position vector of a point on the curve segment. So obviously when I am talking about various 0 to n points, it means actually n plus 1 points on the curve segment, okay. And the bin is a polynomial which we also otherwise know as Bernstein polynomial. And so this is actually the basis function of plotting the Bezier fit component, and the bin as a function of t can be mapped as the combination of ni times of t to the power of I 1 minus t to the power of n minus I. That is how you are plotting the or formulating the basis function known as the Bernstein polynomial in this particular case. So obviously now the expansion of this polynomial can be carried out by opening the combination. So Cin or C, let us say we call it Ni, n is the higher index term which is there. So Cni is actually the binomial coefficient and it can be expanded as n factorial by I factorial times of n minus I factorial from common mathematics knowledge. So therefore Vt, the polynomial, can be written down again as a sigma I varying between 0 to n for the n plus 1 control points factorial n by factorial I times of factorial n minus I t to the power of I 1 minus t to the power of n minus I vi, where these i's indicate the different points, or I would say different coordinate points, which will be useful for plotting the Bezier fit. So the situation is something like illustrated here, that let us say we have a set of n plus 1 points starting between V0, another point somewhere here V1, another point maybe somewhere here V2, then probably somewhere here which is V some point I maybe, and then all the way to V, let us say n minus 1, and finally Vn. Okay. So these are the different n plus 1 points in space. If we just connect them with a broken line, because they are not in totality, the representation is only limited to a few points, okay, here, although the number of points are n plus 1. So we use a broken line to connect all these. So the Bezier ultimately, which would get formulated on the Bezier fit, would look something like this. Between the different points, and the mere variation of such points here would have a curvature variation in a local domain, which can be used to create again a family of curves which can be fitted to the realistic situation. So that is how the Bezier fit is achieved. Okay. Let us work out a property based study of what are the different aspects associated with this particular fit. So let us just first of all try to summarize by saying that the curves would pass through the first and the last control point. You can see here that the curves are passing either through V1 or this V4 here. Incidentally, for the first polygon, which is this particular polygon, the fit is between V1 to V4, and for the next polygon, which is let us say this particular polygon, the fit starts between V dash 1 to V dash 4. The dash merely indicates just a different notation of representing different points, and do not confuse it as a slope or anything in this particular case. So here what the Bezier fit is trying to show a sort of continuity between 4 points which has been used to fit one section of the curve, and 4 points which is being used to fit the next section of the curve, as a sort of a continuous relationship between these 4 sets. So the curves pass through the first and the last control point V0, and in this case n is equal to 4. Okay, so in this case it starts from V1 and V4, and this again starts or originates from the preceding function. So the preceding function in this particular case was this, and there is a C1 continuity, meaning thereby the slopes are same, although the center of curvature of both the curves may be different. Okay. So there is some degree of flexibility in that aspect, and so there is a C1 continuity of connection between these two different convex hulls. Okay. And in the figure on the left, and another thing is that you can correspondingly vary the V in a manner so that corresponding to t equal to 0 and t equal to 1, it represents the first and the last point, which are essentially to be included within the curve. Okay. It is not necessary that you include the remaining points. And in the figure on the left, the starting point V dash 1 of the second curve and the end point V4 of the first curve have the same position coordinates. Okay. So in such a case, if the tangents were supposing or supposedly defining a C1 continuity. Remember, C1 continuity means that same slopes across the connect, but not necessarily the same center of curvature. So, but different center of curvature. You can see, for example, here the center of curvature of this end, for example, of the curve is somewhere here, and that on the other end is probably somewhere here. Okay, so the CCs are different. Only what is important is that the slope of both the curves in both the directions are same to each other. So the slope here at v dash 0, I would say v dash 0 is the first part, or the slope at the first part of the curve should be equal to n times of v1 minus v0. I am going to prove this expression in the next subsequent slide. Okay, and v dash 1 is actually equal to, again, n vn minus 1, where the v1 minus v0 and vn minus vn minus 1 define the first and the last segments of the curve polygon. Okay, so this implies that by aligning the last control point of the first Bezier fit, okay, the connection point and the first control point of the next curve fit results in a C1 continuity between the two curve segments. So slope at the 1 of the last curve should be equal to the slope at the 0 of the succeeding curve. That is what the goal is. So let us now try to arrive at these two conditions mathematically and see, by putting the Bernstein polynomial function and trying to find out what is the v, whether we are able to hit upon this condition here. So let us look at v dash 0 and v dash 1 and how they would be obtained mathematically or numerically. So let us assume a case equal to 3 different points or 4 different points with n varying between 0, 1, 2 and 3, and we want to write down the vector position, the parametric form of the vector position of the fit equation, which is Vt equal to sigma I varying between 0 to 3 C31, okay, combination 3 1, n now mind you is 3, therefore I am substituting the value of n in all the cases, times of t to the power of I times of 1 minus t to the power of 3 minus I times of Vi. So that is how, corresponding to n equal to 3, you can define the Vt. So if I express this function in terms of V0, V1, V2 and V3 separately and just sort of open it up, the way we can represent this whole thing becomes equal to Vt equals C31, the first term, times of obviously t to the power of, sorry, we start with 0, so C30 times of t to the power of 0, 1 minus t to the power of 3 V0 plus C31 t to the power of 1, 1 minus t to the power of 2 V1 plus C32 t to the power of 2, 1 minus t to the power of 1 V2 plus C33 t to the power of 3, 1 minus t to the power of 0 V3, and that is how we kind of shape this thing up between all the different points. Further, if we try to sort of expand this a little more carefully, we would be just eliminating the power zeros, and we have C30 1 minus t cube V0 plus C31 t times of 1 minus t to the power whole square v1 plus C32 t square 1 minus t v2 plus C33 t cube times of v3, as you can see here. Okay. Obviously, we have to also find out what is v dash t. So, the v dash t in this particular case would actually become equal to C30 thrice 1 minus t square with a minus sign v0 plus C31 times of 1 minus t square plus t times of 1 minus t. This would be there would be a negative sign in between. So, minus t times of 1 minus t times of v1 plus similarly C32 times of twice t 1 minus t minus of t square times of v2, okay, plus C33 3t square v3. So, that is how you define the v dash t, and if you correspondingly put the value of t equal to 0 and t equal to 1, so that the end points emerge out of it, and if I substitute this value here, so the v dash 0 corresponding to t equal to 0 now comes out to be equal to C31 v1 minus 3 times of C30 v0. The remaining other expressions involving t would automatically get eliminated, okay, because t equal to 0, and therefore, this can also be represented as 3 factorial by 2 factorial 1 factorial v1 minus thrice of 3 factorial by 3 factorial 0 factorial v0. In other words, it is 3 v1 minus 3 v0 or 3 times of v1 minus v0, and we already know that this corresponds to the index n. So, you can have n times of v1 minus v0 to be defining the v dash 0 in one instance, and in a similar manner we can actually suggest, or we can actually try to define the other expression where we talk about v dash 1, and if I just put v dash 1 in this particular expression here, so all with 1 minus t would get eliminated, and the ones which would have the individual t would be retained, okay. So, the only thing which would be available to us is C32 minus 1 times of v2 plus C33 times of v3. So, this becomes equal to factorial 3 factorial 30 factorial v3 minus, and so you have a 3 here, okay. So, 3 times minus of factorial 3 by factorial 2 times of 1 factorial v2. So, in this case this comes out to be equal to thrice v3 minus v2, or this can be represented as in a generic manner n times of vn, which is the last point, minus v n minus 1. So, as you can see here, the various v dash 0 and v dash 1 corresponding to the first point and the last point of a particular curve section in one case are equal to n vn minus 1, and another case equal to n v1 minus v0. So, in a nutshell, just going back to the earlier slide, as you see here, for the first convex hull, I am just going to rub off a few things here for just for the benefit of clarity. So, in this particular case we are starting to plot two set of points. Okay. One set starting between V1 all the way to V4, okay. Another set which is starting between V1 dash all the way to V4 dash. So, obviously in this particular curve segment 1, which is corresponding to this convex hull indicated here, okay, between V1 to V4, the last point corresponds to the slope at the last point corresponds to V dash 1. Obviously the t equal to 0 at the first point, t equal to 1 at the last point, and this happens to be equal to n times of Vn minus Vn minus 1, as you had just seen in the last derivation. And for the second convex hull corresponding to the points V1 dash to V4 dash, okay, the slope at V1 dash is corresponding to the slope at t equal to 0 for this new convex hull, which is actually equal to n times of V1 minus V0. Okay. So, in order to ascertain the C1 level of continuity, obviously the V dash 1 has to be equal to V dash 0. So, V dash 1 obviously is for the first set of the points, and V dash 0 is corresponding to the second set of the points. So, this is something that you have to be careful when you try to do a practical example problem. So, we want to just solve a practical example of a Bezier fit, where we want to develop the equation of a Bezier curve. We'll try to find out intermediaries or intermediate points corresponding to t equal to 0, 1/4, half, 3/4 and 1. So, we are splitting it up into 0.25 increments, and we plot the curve for the following data points. Coordinates of 4 points are given, V0 to V3, and these are only a two-dimensional curve, because you can see the z coordinate to be 0, and so basically the curve is on the xy plane, and we want to find out what is the functional fit between these points, and also map corresponding to the different values of t for the function.